Welcome back, ladies and gentlemen. This is our last video for AP Statistics. We are on 12.3, day 3, performing a significance test for the slope. By the end of this lesson, you'll be able to perform a significance test about the slope beta of the population true regression line. At the end of this lesson, go ahead and try this last assignment. Let's begin. All right, so as stated, we are in 12.3, day 3, significance test for beta. And you can watch much of this information on the listed AP videos. And you can read much of this information on pages 826 to 829. All right, let's start with the question, what is the formula for the standardized test statistic for a test about a population slope? And is it on the formula sheet? And what about the degrees of freedom? All right, so our test statistic is going to be T, because a lot of things about this line deal with means, so we might as well use T for this. Now, our test statistic is going to be our statistic minus our parameter divided by standard error of our statistic. So in this case, we're looking at our statistic of sample slope minus the population slope that we're going to assume in our null hypothesis, divided by the standard error of our statistic. Degrees of freedom are going to be n minus 2, just like we had with our confidence interval. And just the general formula with statistic minus parameter divided by standard error of statistic on the first page, and the standard error formulas are actually shown on the formula sheet. Now, what is the usual null hypothesis for a test about a population slope? Well, usually we're going to assume that there is no relationship until we can prove otherwise, because we're trying to prove a relationship. So if we're going to assume that there's no relationship until we can prove otherwise, we have to use a population slope of 0 for our null hypothesis, because that is the slope of no relationship. So the usual null is beta is equal to 0. So beta equals 0 is equivalent to using the mean of y for our prediction instead of least square regression line. All right, think about how we calculate our squared and the meaning of it, and the fact that if you flatline this, you have no relationship. So beta equal to 0 means no association between the quantitative variables x and y, similar to a chi-square test for independence, which uses 2 categorical variables instead of 2 quantitative variables like this one does. So let's go ahead and work through an example for this. So many people believe that students learn better if they sit closer to the front of the classroom. Does sitting closer cause higher achievement, or do better students simply choose to sit in the front? To investigate, an AP statistics teacher randomly assigned 30 students to seat locations in his classroom for a particular chapter and recorded the test score for each student at the end of the chapter. The explanatory variable in this experiment is which row the student was assigned. Row 1 is the closest to the front, row 7 is the farthest away. Do these data provide convincing evidence that sitting closer causes students like these to get higher grades? All right, so we have our scatter plot, we have our residual plot, we have our computer output, and then we have a dot plot of our residuals. So for number 1, describe the association shown in the scatter plot. All right, so in the scatter plot, I would say that the scatter plot shows that there is a weak negative linear relationship between row number and test score. The reason I'm saying weak is that if you convert this percent into a decimal to 0.047 and you take the square root of it, you're going to get a very small correlation coefficient. So square root of 0.047 is 0.2167 approximately. That is definitely in the weak range for correlation coefficient. Plus, look at how much scatter this is. This is almost a circle, but you can still tell that there seems to be a bit of a negative linear relationship here. All right, there's definitely no obvious curve in it, which means that it probably is linear, and the residual plot confirms this, because the residual plot shows no leftover curve within the graph, and it's fairly evenly scattered above and below the the residual equals 0 line. Right? There are also no unusual features within this. Right? So weak negative linear relationship between row number and test score. Now, calculating the correlation, I just did that on the calculator. So r squared is equal to 0.047. Remember, I took this percent, I divided by 100 to turn it back into a decimal, and then I took the square root of both sides. Now, this should actually be negative 0.217. because we have a negative relationship showing here, and the correlation coefficient shows the direction of the linear relationship as well as its strength. So because this is a negative relationship, this should be a negative value. So R is equal to negative 0.217 approximately. Right, that's why I put the negative sign here in front of the square root sign. Now for 3, calculate and interpret the residual for the student who sat in row 1 and scored 76. All right, so I decided to go ahead and define some variables here. I have y equal to test score and x equal to row number. So my predicted y value, my predicted test score, is equal to my y-intercept, which is my constant coefficient, 85.706, plus my slope. Now my slope is negative, and plus a negative just turns into minus, so that's why I have minus 1.1171 times my row number of 1. If you type all of this into the calculator, you will get about 84.5889. This is my prediction. Now the residual is your actual y value minus your predicted y value. The actual y value reported is 76. That's why I'm starting with 76. While my prediction is 84.5889. So that's what I'm subtracting at the end of this. Remember, actual minus predicted, we are in AP. When you complete the subtraction, that equals about negative 8.5889. So I have calculated my residual. Now I need to interpret it, and that's for this sentence. So the student who sat in row 1 scored 8.5889 points less than predicted by the least square regression line with x equal to row number. All right, so the actual score of the student who sat in row 1 is about 8.5889 points lower than the score predicted by the least square regression line. Notice that 76 is lower than 84 point something. That's how I know to use the phrase less than. Okay, let's go ahead and take a look at number 4. And this one is asking us to interpret the slope of the least square regression line. Now again, remember, the slope is the change in y over the change in x, which means that the slope value goes with the change in your prediction, while the change in x is always going to be a change of 1 because you're dividing your slope by 1 to turn it back into a fraction. So the predicted test score goes down by about 1.1171 points for every 1 row added to the student's row number. Right, so our prediction for test score decreases by 1.1171 points for every single row added to the row number. For number 5, let's explain why it was important to randomly assign the students to seats rather than letting each student choose his or her own seat. Now, the key for this is what we were asked to do at the beginning. Does sitting closer cause higher achievement? For cause and effect, you need a well-designed randomized experiment. And the treatments that were being assigned was which row number the student was sitting in. So the goal is to determine if there is a cause and effect relationship between test score and row number. This requires randomly assigned treatments in a well-designed experiment. Since seating is the treatment, it must be randomly assigned. And that ties into number 6. What other variables did the teacher control, and what was the purpose of keeping these variables the same? So this is a little bit of review from chapter 4. So things that the teacher controlled was the teacher gave the same test to all the students, had the provide the same instructional time, had the same teacher, same chapter. All of those things that the teacher kept the same were variables that the teacher controlled. Now the teacher introduced this level of control to reduce the variation in the test scores that is due to factors other than seat location. All right, this is going to increase R squared and decrease the standard deviation of the residuals and the standard error of the slope, making it easier to find convincing evidence of an association. Basically, it increases the power by decreasing the variability. Right, so for number 7, is there convincing evidence that sitting closer to the front improves test scores for students like these? Well, let's check it out. For our statement, we want to state our hypotheses, define our parameter, and then identify our confidence level. All right, so my hypotheses, my null hypothesis is going to be beta equals 0, basically assuming that there's no relationship first, versus what I want to prove, which is my alternative hypothesis, that beta is less than 0. Basically, as students sit further away from the board, we're trying to prove that they score less. All right, now this is where beta is equal to the slope of the true least squares regression line relating y equals test score to x equals row number for students like these, using alpha equals 0.05. Now it is important to write down for students like these because we didn't randomly select from the population, which means that our cause and effect relationship is only really valid for students very similar to the ones in our study. Now the evidence that we have to actually make us go further with this test is that the sample slope of negative 1.1171 is less than 0, so that is on the correct side for our one-sided test. Now our plan is to use a t-test for beta, so we need to check our conditions. First we check linear, and our residual plot over here showed no leftover curved pattern, which means that linear is appropriate. For independent, knowing the score of one student won't help predict the score of another. For normal, dot plot of the residuals shows no strong skewness or outliers, as you can see here. Equal standard deviations, there is no clear greater than or less than pattern in the residual plot. So the residual plot is fairly evenly distributed above and below the residual equals 0 line. You could also state it that way. And for random, the treatments were randomly assigned, so all of our conditions are met. Now for our do step, we need to go ahead and calculate our test statistic, and then we'll find our p-value based on that. So our test statistic of t is equal to our sample slope minus the assumed population slope from our null hypothesis divided by the standard error of the slope. Now our sample slope was negative 1.1171. Our standard error of our slope was 0.9472. And we are assuming that beta is equal to 0 based on our null hypothesis. So that's why I have negative 1.1171 minus 0 divided by 0.9472. Now that equals about negative 1.179. All right, so that's my t. Now the degrees of freedom are my sample size minus 2. I had 30 students. Minus 2 gives me a degrees of freedom of 28. Our p-value is going to be the probability that we have a test statistic of t less than negative 1.129. Now, the reason that I know to go less than is that that's the direction of my alternative hypothesis, and that direction of my alternative hypothesis is based on increasing rows, making students get lower grades, which is basically the flip side of the coin from sitting closer causes higher grades. That implies that sitting further away causes lower grades. That's why I'm using this less than here. All right, so I'm going to use TCDF, and because I'm going less than, my lower bound is going to be negative infinity. My upper bound is negative 1.129, degrees of freedom 28, and if you put that into the calculator, we're going to hit second vars to get to distribution. Go down to TCDF. Lower bound is negative infinity. It's already defaulted to that, so I'm going to go down to upper bound. My upper bound is about negative 1.1. That should be 179, I believe. Let me just double check my calculations here. I'm finding discrepancy in my work. Whenever you find that, check your answers. Negative 1.1171 minus 0 over 0.9472. As you can see, teachers sometimes have these issues also. All right, so it was negative 1.179. So I need to fix this. As I said, teachers have these issues also. And yes, you guys get to see me completely raw with this so that you know that it's no big deal. You find it, you fix it, and you move on. So again, I'm going to go to second vars to get to distribution. I'm going to go down to TCDF, and I'm going to keep that negative infinity. I'm going to use negative 1.179, degrees of freedom 28. Paste this in, and I have about 0.124. All right, so I had put it in the calculator correctly. I just accidentally wrote the wrong number. All right, so for our conclusion, because the p-value of 0.124 is greater than our alpha of 0.05, in other words, it's not less than or equal to like we need it to be, we fail to reject the null hypothesis. There is not convincing evidence that sitting closer improves test scores for students like these. Now, the last little bit that we're going to take a look at is, what is p-hacking? Now, we've taken a look at this previously, but p-hacking is testing for associations between many different variables until you find one with a p-value less than 0. All right, so testing between a whole bunch of different variables until you find one with a p-value less than 0. And I'm going to go ahead and, let's see. Yeah, you can go ahead and take a look at these links in our Google Classroom. Go ahead and try this assignment, and I will see you in class.